Last lecture we covered the Reits representation theorem. So that says that any continuous linear functional on a Hilbert space is representable by a vector. Another way of saying that is that Hilbert space is a self-dual. And I argued, at some length, that it's this self-duality which picks out Hilbert spaces as being some analog of finite, maybe finite dimensional if you like, but not strictly speaking finite dimensional. So there's some kind of finite objects in this world of infinite dimensional function spaces, and that's why they're well behaved, and they are well behaved, as we'll see. Okay, so this is one of the virtues of Hilbert spaces. We discussed orthogonals last lecture. That's just some terminology. So what I want to do today is, first of all, prove that L2 spaces are Hilbert spaces. And that will get us the advertised self-duality of L2 spaces. And then hopefully there's time also to start on the material on orthogonal bases. So what's the point of that? Once we know these are Hilbert spaces, we might want to actually understand one example in some detail, right? So what does it mean to compute this space, to really understand everything there is to know about it? Well, in a finite dimensional vector space, suppose it's the space of solutions of a linear differential equation. It's easy to see that you give me any linear differential equation, its space of solutions is a vector space. Well, big deal, that's easy. That doesn't mean you understand anything, right? To actually understand that vector space is to compute a general solution, right? That's a basis for that vector space. Once you've computed the general solution, then you actually know what the hell you're doing with that vector space. So similarly here, just because we can talk about this as a Hilbert space, which we will in a second, doesn't mean we really understand squat, right? However, we do know quite a bit about the space of functions on S1. Namely, we know trigonometric polynomials, we know trigonometric polynomials are dense, and that will tell us, in fact, something called an orthonormal basis of the L2 space. And once we've got that, we really know what we're doing with this space, and that's essentially the same content of knowing about the Fourier transform. So that's what I want to do at the end of today's lecture and next lecture. I'd originally intended to give a bit of an exposition on the uncertainty principle and what it has to say about spaces from the point of view of L2 spaces. But we're not going to have time for that. So what I'm going to do is have some sort of bonus lectures, which I'll schedule either next week or the week after, and you can come if you like. If not, good for you. So they won't be examinable, but I want to tie up some loose ends. Okay, so that's the plan. So what have we got to do to prove that L2 spaces are Hilbert spaces? Well, we know they're vector spaces. We know they're normed spaces. So I just have to tell you what the pairing is supposed to be and prove that it satisfies the axioms. All right. Well, also I have to deal with the fact that previously I talked about real valued L2 spaces primarily. So in the complex valued case, there's not much difference. Right, so as usual, we start with an integral pair. So let P and Q be dual exponents, so P and Q both greater than 1. Now, the integral in my integral pair knows how to integrate real valued functions and give you real numbers. Well, as I've discussed, just take a complex valued function and integrate its real and imaginary parts separately, and that defines this symbol when it's taking as input complex valued functions. So then given a g, I can integrate against the conjugate of g to get a continuous linear map from this space to F, continuous with respect to the norm coming from the P norm. All of that is immediate from what we already discussed for the real valued case. There's nothing new here beyond what we've already discussed. Well, except for the fact this is clearly not linear, right? As I've written it at the moment. I need to put a bar somewhere because G goes to L of G bar, which if I multiply G by a scalar, I'd get a conjugate out the front. So wherever, it doesn't really matter. Anyway, so that map is conjugate linear and bounded. Okay. So by the universal property of the completion, there is a unique bounded linear map phi qp, making the following diagram commute. So here's, ultimately we care about p equals q equals 2, but I might as well do it for all dual exponents for the moment anyway. Okay, so that's iota, that's the completion. Well, let me just drop the norms. So this is the q completion with respect to the q norm. Okay, so then I could take the completion of CTS XF with respect to the P norm, that's iota P. So that goes from CTS XF to LP XF. Then taking the joule of that gives me a map from the joule of LP to the joule of CTS XF. That's an isomorphism, and this is that's the isomorphism. And I mean, these conjugates just come along for the ride. There's nothing happening with the conjugates. Okay. So what I get is this map here. All right. So that's just upgrading what we've already discussed to the case of complex valued functions. Okay. I mean, maybe it's worth saying, what does that mean? What does commutativity of that mean? It simply means that if f and g are both continuous functions, then phi qp of g of f, right? I mean, phi qp can eat anything in LQ, which is some limit of things which are continuous functions, but in particular, it can eat things g which are not continuous functions, right? Similarly, f doesn't need to be a continuous function. But if they are both continuous functions, well, then this is just this. That's all commutativity of that diagram says. It says that if you restrict g and f to both be continuous functions, it's just the integral. All right. So that means that I can take a pair, f, g, and associate to them this element of f, which is just obtained by evaluating phi qp on g, and then evaluating that on f. All right. Well, what I just said tells you how to evaluate this. So remember that you're supposed to think of CTS XF as sitting inside here as a dense subset, right? And it also sits inside there as a dense subset, but with respect to a different topology. Okay, but if I feed in an f and a g which belong to those dense subsets, then the output of this pairing is just the integral of f with the conjugate of g. Okay, so that's easy. So to understand this pairing, we just have to figure out how to evaluate it on things which are limits of continuous functions and not necessarily themselves continuous functions. That is, we need to understand something like that. So to be clear, here the fn's and gm's are actual continuous functions. And what I mean is take a point in this space. Any such point is a limit of a sequence of things in CTS XF with respect to the P norm. Okay, so it looks like that. Similarly, anything in LQ looks like this. And well, I claim you can just sort of do the obvious sort of thing. So maybe this double index limit looks a bit weird. Well, what do I mean by this double limit? I mean, here I've got an element of f indexed by m and n. So I'm claiming that if I fix n, that's a sequence indexed by m. I claim its limit exists, and that the sequence of those limits has a limit, and that's this. And similarly in the other order. All right. All right, so that reduces the computation of such a pairing to just computing integrals of continuous functions. All right. So let's write f for this limit and g for the other limit. Well, then, so by definition, the pairing is the value of this thing which was produced by that universal property. Okay, so, but this thing here, so that's an element of the top right corner of that diagram, which, I mean, forget about the conjugate line. That doesn't do anything for our purposes at the moment. So this thing I've underlined in green is by definition a continuous linear function from LP to F. And now I've just fed in a sequence. Well, if it's continuous, then I can take that sequence, which it is, then I can take that sequence out the front. All right, so I've got this as a limit in F. Okay, so now we use one of the exercises, which is that if I give you a normed space, then a map which sends a vector to evaluation at that vector, well, it's well defined. In particular, its image is something which is continuous on the dual. Okay, so if I fix an element of V, which in this case is LP, then evaluation of that element is an element of LP dual dual, which is to say it's a continuous linear map from LP dual to F, which is what I just said. So it's continuous, which means that phi QP of G of Fn, so now I'm imagining n is fixed. Well, that is by definition just the evaluation at Fn of phi QP of G. But now G is a limit of things. All right. And phi QP is continuous with respect to the obvious norm on the left and the operator norm on the right. And the operator norm is the thing with respect to which evaluation at Fn is continuous. So continuing that calculation, that's evaluation at Fn of the limit of m. And this was using that phi QP is continuous. And then, well, evaluation is continuous as well. And now I'm down to this point on the bottom right-hand corner of that board, right? Because, well, this is phi QP Gn evaluated at Fn, but those are both now continuous functions. Yeah. Okay, so this term here is that limit over there, and so the thing I want is the limit of those limits. Now, if you just look at that argument, you can see you can do it in the opposite order. Start with the evaluations at Fn, and then afterwards do the limit in the other variable, and that'll give you the other equality there. I don't actually need the other equality anyway for our purposes, so I include it because otherwise it looks strange, but it's not actually necessary. Okay, so that proves the lemma. Maybe that's still a little unwieldy, right, because we've got these two limits involved. You might have guessed, rather, that to evaluate this guy, I would just take the limit over n of Fn gn bar. That would have been a plausible guess also. So let's prove that that's actually correct as well. Any questions about this first? Now, why are we doing this? Well, if we want to prove this thing is a Hilbert space, we better be able to actually compute its pairing so we can prove something about it. Right? I mean, it would be reasonable, and in fact you would succeed if you tried this, to just try and go entirely from universal blah blah to prove that this is actually a Hilbert space structure, but I think it's more instructive to get your hands a bit dirty at this point. Okay, so let me state a technical lemma, which I'm going to skip proving. So that's the situation we've got, right? We've got a doubly indexed family of scalars in F. And let's suppose that the limit in, let's say, this order exists. Again, that is to say that if I fix M, then that limit exists, and that sequence of limits has a limit which is L. And I also need to assume something about the convergence of these sequences with respect to changing M. It's something like uniform continuity. And let me say precisely what I mean, which is that for all epsilon greater than 0, there exists a K So what's that saying? Well, I know all those sequences converge, but I don't know that they converge sort of equally quickly, right? So it may be that for some values of M that converges really fast, and for other values of M it's much slower. And it could be that that convergence is, there's a conspiracy of those rates of convergence which prevents the following, which is what I want. I mean, what you should think about is, think about these guys arranged in a grid, which goes off infinitely that way, that's n, say, and infinitely that way, that's m. And what I'm saying is, if that entire thing, if I go limits in one direction and then limits in the other direction, I'm saying I might as well have just taken the limit along the diagonal. But that doesn't have to be true. If there's, as I said, some conspiracy, that could avoid being true. All right, but this prevents the conspiracy. Right. Okay, so this is what I want. And well, it's a short argument in the notes once you figure out what you're doing, but I'm going to skip it. All right, so what's that tell us? It allows us to deduce that in this situation, so in the situation as above, that is P and Q dual exponents and so on. But I can reduce this to a single limit. Okay. All right, so let's do the proof. So unsurprisingly, AMN is going to be the integral over x fmgn bar. Well, no. Okay, so that's my sequence. So what are we going to do? I mean, to prove this, I just need to check this hypothesis, right, for these integrals. Well, those numbers there are phi qp of gm of fn, right? Well, G, the sequence GM converges in LQ. So the image is therefore convergent. In particular, it's Cauchy with respect to the operator norm. So that tells me the following. It tells me that given a delta greater than 0, which we'll determine in a second, we can find K such that for all m and m prime greater than or equal to K, the operator norm of phi qp gm minus phi qp of gm prime is less than or equal to delta. Right? That's what it means to be Cauchy with respect to the operator norm. That's the operator norm. Okay, well, then for any n, provided the norm of this with respect to p is non-zero, I mean, what does the operator norm being less than something say? It says that if you evaluate the functions inside and take the norm, that it's less than guess I don't need to be paranoid about that. Okay, so that operator norm being less than that says if you evaluate this linear operator on anything, the norm in f of that output is less than this thing times the norm of the input. But this is exactly the difference between a m n and a m prime n. So I need to show that I can make that less than epsilon, given an epsilon. Well, if the norm of f is 0, it's easy to see that everything works. So let's suppose it's non-zero. And then, well, I mean, what do I mean? So I mean the norm of f, right? So f is fixed. That's the limit of the fn's as earlier, right? So let's suppose the norm of that limit in LP is non-zero. So that means that for sufficiently large n, the norm of fn can't be 0 either, right? Because it's continuous. Okay, so let epsilon be such that, well, sorry, that's given. right? When we're proving this inequality. So epsilon is given. And choose k such that for all n greater than or equal to k, fnp is less than fp plus epsilon. I mean, that's possible, right? Because those guys converge to this. So we're given epsilon, we find this k, and then we set delta to be that epsilon divided by that number. Now that's not 0, so this is all right. And increasing k if necessary, we have the following. We've got am n minus am prime n. Well, that's less than that. But that's equal to fnp on fp plus epsilon times epsilon, and that's less than 1. So why was the proof architected the way it was? Well, I can't take an n in here, right? I mean, this needs to be something which depends only on epsilon. So that's why I arranged it this way. But anyway, so this is a number which is less than 1. Okay, so that proves the hypothesis of the lemma, and therefore we get the conclusion. All right. So now let's use that to prove that L2 is an LP space. Sorry, did I just say prove L2 is an LP space? I mean Hilbert space. Okay, so it's a complex vector space. This pairing, well, now we know, I mean, I defined it in some abstract way, but now we know we can compute it just by taking limits. All right, so if you like, take that as the definition. Okay, so I claim that that pair is a Hilbert space. So what have I got to prove something's a Hilbert space? Well, I have to prove this thing is linear in both variables, but I mean, this thing is a topological vector space, so addition and scalar multiplication are continuous. The integral commutes with addition and scalar multiplication, so it's clear looking at the formula that it's linear in the first variable and conjugate linear in the second. So the linearity is clear. All right, so that leaves the fact that exchanging the order does a conjugation on the right-hand side. So but I mean, conjugation is a continuous operation on C. So and the way we defined this was to integrate the real part and the imaginary part separately. So if you do the conjugate, that's just tautologically the same as integrating the conjugate. And then, well, okay, so that last step's familiar. All right, so that just leaves checking the positivity properties. So F. that's the limit as n goes to infinity of the 2 norm of Fn. And we know that the norm is continuous, so that's just this, which is that. Now this we already knew, right? Because we already knew L2 was a normed space. We proved that. So what we've done now is show that underlying this pairing is the original norm. That shows that this thing is 0 if and only if f is 0 by the properties we already proved of the norm, and similarly that's always non-negative. Okay? So that proves the other properties of a Hilbert space, so we're done. Okay. Thank you. Yeah. All right. So that's a Hilbert space, and therefore we get the isomorphism which is integration against G. Okay, any questions about that argument there? All right, so there's a part in the notes for lecture 20 which I'm going to leave to the tutorial, which is the argument. That's sort of an extended example, if you like, which is an argument for how to construct vectors in here from integrable functions, right? So a priori, you may have seen this if you've encountered L2 spaces elsewhere in your courses. You will have seen some description of L2 spaces as some functions satisfying an integrability condition, not necessarily continuous, modulo a relation. The way we've presented it is not like that. This is a completion of something. But integrable functions naturally give you continuous linear functionals on L2, and by this isomorphism, they therefore give you vectors in L2. So that's how to see that any integrable function, Riemann integrable, Lebesgue integrable, gives you a vector in L2. So that's how to connect those 2 points of view. And as I said, that'll be developed in detail in the tutorial.